Hello and welcome again to my physics online video lecture series. In today's video we're going to be continuing our discussion of vision from a physics geometric optics perspective. In this video we will be discussing vision correction, specifically vision correction using eyeglasses and contact lenses and the like, not surgical attempts to correct vision. We're actually focusing a little bit narrowly in this one just on correcting nearsightedness and farsightedness and presbyopia. Okay, so I'm not trying to focus on or discuss surgical techniques for correcting vision, stuff like LASIK, in which what you essentially do is reshape the eye's lens by ablating part of it with a laser. And so you basically like reshape it so that it has a better accommodation limits. I'm not focusing on trying to correct vision problems like astigmatisms, any kind of anything where you need like double focal length type or bifocal glasses or cylindrical lenses to deal with stuff not focusing to a point in your eye where you get like the little line in your vision. I'm not trying to discuss any of that stuff. I'm mostly just wanting to discuss correcting nearsighted and farsighted using eyeglasses. So to do that, we can begin by our little review. So recall a few key points from the previous lecture about accommodation. So first thing is accommodation gives you kind of what is the range over which you can see. The accommodation limits are determined by how close your near point is to your eye, how far away your far point is from your eye, and they are related to what kind of power your eye's lens has for focusing. So typical values for near point and far point are 25 centimeters and effectively infinite distance away respectively. So if you cannot see stuff that is close to you, then you are what's called far-sighted, or you have hyperopia. Maybe your near point is actually 1 meter away rather than 25 centimeters away. If you're nearsighted or if you have myopia, then you can see things that are close up just fine, but you can't see things that are very far away very well without correcting your vision. They're very blurry if it's far away. And so maybe your far point is 3 meters away instead of 1,000 meters away or whatever. The other thing to know is that your eyeball's thickness, a typical value for the thickness, is about 2 centimeters, and that this right here also is the image distance for the eyeball. The equation that we have been using with the eyeball is of course the thin lens equation, and we will actually use a similar equation today for correcting vision. So again, the two types that we're fundamentally trying to correct are nearsightedness, which is sometimes also called myopia. This is a Y for what it's worth, myopia, and then far-sightedness, which is sometimes called hyperopia. And presbyopia, for what it's worth, presbyopia basically is a kind of a form of this far-sightedness. Basically, your near point moves farther and farther from your eye as you get older and older. So in nearsightedness, your far point has also shifted nearer to you than what is ideal. So instead of being able to see things very, very far away, your far point may be only 1 meter away or a few meters away or what have you. And then if you're farsighted, your near point has shifted to somewhere farther away. In this case, your near point has shifted to be farther away than sort of the ideal 20 to 25 centimeters or shorter for younger people. So your near point may be 50 centimeters. So that's not too terrible, but not great. It could be a meter away. It could be 2 meters away. It could be a few meters away, etc. And so you need to correct that. Obviously, nearsighted people, without vision correction, you can read a book or something up close, not a problem. Anything you're doing like really in close, not usually a problem. But activities that involve anything farther away than 1 or 2 meters starts to be very blurry, kind of makes sports hard, makes driving hard, that kind of thing. And then on the flip side, if you're farsighted, you can do stuff far away, but anything up close becomes difficult. Same with presbyopia. Stuff that's up close becomes difficult. You can't hold a book here and read it. You see sometimes elderly people, but farsighted people in general, if they don't have glasses, they may be like holding the book way out here to read it because their far point has moved so far away. So how do we correct these? Oh, I should also mention it's possible to have both nearsightedness and farsightedness simultaneously. For that, you would end up needing a set of bifocals. Essentially what happens in this case is your near point is farther away than 20 to 25 centimeters. Maybe your near point is a meter away or something like that. And on the other hand, your far point is not so far away. So maybe your far point is 4 meters away. Okay, so your eye's accommodation is you can see stuff between about 1 and about 4 meters clearly, but anything farther away or anything closer up is blurry. So even that can be fixed using bifocals, but I'm going to focus on fixing one thing at a time. So how do we fix vision? With eyeglasses, with contact lenses, whatever. Well, the fundamental process is the same in all cases. Basically, your glasses or contacts create an image of the object that you're trying to look at, and that image is placed within your accommodation limits. So it's within your eye's accommodation limits, and of course the image has to be upright and therefore virtual. So, for example, if you have accommodation limits, you're farsighted so that you can't see anything closer than a meter away, and you want to correct your vision, you have an object that is 25 centimeters away. You want to be able to see that object because that's sort of like normal vision. What the glasses do is they take that object that is 25 centimeters from you and they make its image so that it's more like 1 meter away from you. So the image is formed farther away. It's at the near point of your eye. Now note that by making the image be a meter away from your eye, it's not saying that it's a meter away from the glasses. There's a distance between the glasses and the eye that also has to be accounted for. With contact lenses, that distance is pretty well negligible. So here's kind of like a conceptual drawing of that to correct for somebody who is farsighted. They can't see an object that's 25 centimeters in front of their eye. All right? They can't focus on it. Their near point is 1 meter away. So what the glasses do is they image the object that is 25 centimeters away so that it appears to the eye as if it is 1 meter away, where the location of the near point is for that eye. It should be noted that by changing your near point, you may also effectively change your far point. How does that work? Well, in the case of this correction, where we have somebody who's farsighted, you end up having to use a convex lens and it moves your image to farther away. The image of the object is farther away than the object was. If you have this lens and it has a focal point, say out here somewhere, any object between the lens and the focal point will form a virtual image, which is fine. You have an upright virtual image. But if you have an object that's farther away than the focal point, then that object will form a real image, which means that the image is being formed on this side of the lens. And so essentially you'd have an upside down image. So basically your glasses will correct this problem, but they will create problems for things that are very far away. And so sometimes you'll see people like looking over the top of their glasses if they want to look at something farther away. Depends of course on like where the focal point is. And the flip side to that is that if you want to correct far-sightedness, if you want to correct nearsightedness, you use a convex lens, and so that basically images everything to be nearer than what it otherwise would have been. And so that will tend to move your effective near point to somewhere farther away as a result. So when you correct this right here, farsightedness, you move your effective near point closer into you, but you also change your effective far point so that it's closer. If you correct for something that is nearsightedness, essentially what ends up happening is you move your effective far point to farther away, but you also move your effective near point to farther away. Again, you have to account for this distance between the lens and the eye when doing all this. So in looking at these are all given with respect to the eye. If you want with respect to the lens, this basically like DO becomes 25 minus delta x, and this DI becomes 1 meter or 100 centimeters minus delta x as well. Thus, if your glasses sit, let's say, 3 centimeters in front of your eye, then the object, which is at 25 centimeters from your eye, is only at 22 centimeters from the glasses, and the image, which is 1 meter from your eye, is only 97 centimeters from the glasses. Alright, let's work an example to sort of conclude this lecture. So let's say that you've got a friend who's nearsighted, and her near point is 20 centimeters from her eyes, and her far point is only 150 centimeters away, 1.5 meters away. Okay, so we're talking somebody whose far point is a little under 5 feet from their eye. They can see stuff 5 feet away but no farther clearly. We want to correct, or she wants to correct her vision using some glasses. And she's going to wear her glasses. The glasses are going to sit on her nose. There's going to be some distance between her eyes and those glasses, maybe 1 inch, like 2.5 centimeters of distance. And so what we want to know is what power do we need for those glasses if they are to correct her vision? So how do we work this problem? How do we break this down? Okay, so for this first part, the what power, this is power, recall, is defined as 1 over focal length. Unit of diopter is the same as 1 inverse meter. Okay, so this means that this right here is 1.5 meters. Now her glasses are 2.5 centimeters from her eyes. Alright, that means that the delta x from this diagram here, this delta x, this is 2.5 centimeters, which is the same as 0.025 meters. This right here is actually going to give us the far point. Okay, it's going to give us the image distance, but we know that the image is on the same side of the lens as the object. We know that that's going to be the case. So this means that her image distance will actually be negative. And essentially what this is that DI will equal negative of 1.5 meters minus 0.025 meters. Basically this distance for the far point minus the delta x. And so di is negative 1.475 meters for this problem. Now we can proceed with the problem itself. 1 over dO plus 1 over di is equal to 1 over f, or is equal to the power. We didn't specify what dO is. Well, we're looking for the far point. So dO, basically what we're trying to do is take something that is infinitely far away and image it so that it's 1.5 meters from her eyes. So dO is essentially a very large number, like infinitely far away or 1,000 meters away, something like that. So basically what that means is that this 1 over dO term is essentially 1 over infinity. So this 1 over dO term is approximately 0. If you have 1 over infinity, you have basically 0. Okay, so that means that the power is just equal to negative 1 over 1.475 meters, and that is equal to about negative 0.67796. So let's call that negative 0.678 diopters. So that is basically the power of the lens that we need. Now the other part of this problem is talking about what if we want to know where this thing is being imaged to, if it is her near point. So in other words, the second part would be what is her new near point, and I'm going to underline that in kind of this green color. So in other words, dO is what, in order for the image di, 20 centimeters from her eyes, di is equal to negative of 20 centimeters minus 2.5 centimeters, which converted to meters gives me negative 0.175 meters. So, what is dO to make this the case? And we just found the power here. So power found at the end of the answer is now the same power that we would use here, or the same focal length. So 1 over dO plus 1 over di is equal to the power. That means that 1 over dO is power minus 1 over di, which is negative 0.678 diopters, plus, because this number is actually negative, 1 over 0.175. In other words, we have minus negative or minus 1 over negative 0.75. So if we do that, what we end up getting is that the 1 over dO is about 5.036 inverse meters. Okay, and so that means that the new dO, if I inverse it, the new object distance that will be 20 centimeters away is 0.1985 meters from lens. But we want to know how far from the eye is that, so we have to add to that another 0.025 meters, because remember that the glasses are some distance from the lens. So this is dO equals, it's really dO plus delta x equals, and the answer ends up being about 22.4 centimeters. So notice that that is farther out than her original near point is. So that's all that I was going to do in today's video. I could work another example correcting farsightedness instead of nearsightedness, but this video is already kind of long for how long I try to make these videos. So I'm going to stop there. Hopefully you learned something from it. And as always, thanks for watching.